Este curso de pruebas asistidas por computadoras en dinámica no lineal y pues este curso es un curso enfocado a todos ustedes, estudiantes avanzados, posgrados, postdocs y también a profesores, investigadores interesados en el tema. Y tenemos la fortuna de tener a dos muy importantes investigadores y también muy buenos amigos aquí del departamento, que son Jay Mireles y Jean-Philippe Desart. Primero nos va a dar la primera parte del curso, la va a dar Jason Mireles James. Entonces déjenme hablar un poco de Jason. Pues a Jason yo lo conozco desde hace mucho porque él hizo su doctorado en la Universidad de Texas en Austin y fue alumno de Rafael de la Llave, que fue también mi asesor, y desde entonces estaba trabajando ya en métodos de pruebas asistidas por computadoras, sistemas dinámicos, y hizo bastante trabajo. Cuando éramos estudiantes de doctorado, de hecho Jay también ganó algunos premios por sus calidades didácticas, entonces para ver que es un muy buen expositor. Y después Jay fue a hacer un postdoctorado en la Universidad de Rutgers, estuvo trabajando con varias personas, entre ellos Konstantin Shakov, que también es un experto en estos métodos, y ahora es profesor de la Florida Atlantic University en Boca Raton, Florida. Entonces, por favor, si tienen preguntas, pregúntenle a Jay, pregúntenle en inglés. Si no se sienten seguros con el inglés, pregunten en español y entonces yo puedo traducir o cualquiera de nosotros puede traducir. Pero por favor no se queden con dudas. Jay está en toda la disposición de responder las preguntas que tengan, ¿no? Entonces, okay, Jay, thanks a lot for being here, and then please go ahead.
Okay, thank you. Let me say first, on behalf of myself and Jean-Philippe, what a great honor it is to be here today. I want to thank Renato and Carlos for the invitation and for organizing the workshop and having us here these days. But I especially want to thank, and from the bottom of my heart, to thank all of you for coming to listen to what we have to say today. This is really exciting for us. Yeah? The title of the workshop involves nonlinear dynamics, right? And of course, we'll have a lot to say about nonlinear dynamics in the next few days. But to begin, I want to be a little more specific, a little more focused. I think on some level what this course is really about, it's about solving nonlinear equations. It's about solving nonlinear equations with the help of the digital computer, and ultimately in a mathematically rigorous way that leads to new theorems, again, with the help of the computer and a lot of mathematics. Okay, so I want to start off at the beginning, yeah? And hopefully, you know, this will go at a very easy pace at first. So here's a setup. The setup we'll use all the rest of the week. We're interested in continuous, or better yet, smooth maps between Banach spaces. So let's think about a map F between Banach spaces X and Y. And we want to solve, since we're in a Banach space, it makes sense to talk about a zero. So we want to solve equations like f of x equals 0. Okay? Now you might think of x, it could be an equilibrium or a periodic solution of some ordinary or partial or delay differential equation. It could be a covering map or a chart map for some invariant manifold. It could be the solution of some initial value problem, some boundary value problem. Okay, that depends on what you're doing, right? But in all of those situations, there exist already extremely powerful numerical methods for finding approximate solutions to nonlinear problems. Okay, even nonlinear problems in infinite dimensions. So the question that we like to think about is this. Suppose you have such a nonlinear problem, and you also have in hand a good, maybe a good enough, whatever that means, approximate solution of f of x equals 0. So you know some element of your Banach space x, we'll call it x bar, so that f of x bar is not so big. Okay? Can you conclude given that information, that there's a true solution, a true zero of f of x may be nearby x bar. Okay, and of course the answer is sometimes yes, but it's going to depend on the spaces x and y, the map f, and even on your approximate solution, x bar. Okay? Proving that the answer is sometimes yes, of course you have to make precise what you mean by good enough and nearby, right? So that'll be a big part of the fun as this discussion goes on. Okay, here's a little terminology. So you'd like to have some theorem or theorems which help you answer this main question. Okay, and we'll call such a theorem an a posteriori theorem or an a posteriori existence theorem. Because first, you compute some approximate solution of your problem, then by analyzing your problem and that approximate solution, you try to conclude that there's a true solution, that there exists a solution nearby. Okay, let's start thinking in one dimension, okay? So in one dimension, imagine you have a function, f of x, and you'd like to prove that you'd like to find a zero of f of x, right? So excellent method for doing that is Newton's method, which we all know. You take some initial guess, right? And you look at f of that initial guess. This won't be zero, but hopefully it's not too large. And now you replace the function f of x with its tangent line. And now instead of solving the nonlinear problem you were given, you solve the linear problem, finding where this tangent line intersects, and then you try again, right? So this is our old friend. And now you repeat, yeah? And hopefully if your initial guess was good, this converges to your true zero, right? Okay, so here's a typical kind of theorem that you, in a numerical analysis course, that you would prove. This is what I would call an a priori theorem for Newton's method, okay? This theorem says, imagine that f is C2, and suppose that it actually has a zero, okay? And suppose that the derivative of f at that zero is non-zero. So the theorem says that there exists a neighborhood of your true solution, so that if you pick a point A in the neighborhood and start your Newton iteration with that point A, that the iteration converges, and it actually converges rapidly, right, quadratically fast. Okay? So this is a classical kind of theorem about Newton's method that's telling you what kind of problems Newton's method is good for. Newton's method is great if you have two derivatives, right? If you had only one derivative or zero derivatives, this theorem is saying maybe you don't try Newton's method, right? But this theorem isn't telling you what happens if you've numerically done some work, right? How close are you to the solution, or is there a solution at all? That's what you'd like with an a posteriori theorem. So, is it possible to get an a posteriori result for Newton? And I want to give you kind of a geometric argument, at least in 1D, that I think says why you should be able to do this. Okay, so imagine instead of the earlier picture where you saw the curve and you knew you had a zero, imagine all you know is you have this single point f of x0, okay? And you know, so you can think of this as a point on a curve. Okay, so you're constrained to lie on this curve, but you can't see the curve. All you can see is the value of f at x0. But maybe you can compute the derivative at x0, all right? Which you could think about as the velocity of this point, right? So now if you think about the x-axis as like a brick wall, and you think of this as a particle moving toward the brick wall with some non-zero velocity, okay, the question is the particle going to hit the brick wall or not? Right? You know that the answer depends on how fast can the particle accelerate, right? So if you had some local bounds on second derivatives, and if the second derivative's not too big, then this particle can't bend away from its tangent line fast enough to avoid hitting the wall. There will be a zero, right? Okay, so this is the kind of argument you'd like to make rigorous, to have an a posteriori theorem. Okay, in one dimension you could do it basically just like I've said here, but if you want to generalize this to higher dimensions, it's nice to talk about a little more machinery. So in fact, we'll need a little more machinery. So to generalize this to higher dimensions, to infinite dimensions, we'll use the contraction mapping theorem. So let me just remind you, the contraction mapping theorem says that if you have a map on a metric space, or from a metric space to itself, okay? So first is a definition. We'll say that this map is a strict contraction if the distance between any 2 points is always less than, well, that should be less than or equal to kappa times the distance between the points, where kappa is strictly less than 1. Okay, so this is what it means to say that a map is a contraction. Okay, and Banach's fixed point theorem says that if X is a complete metric space, and if F is a contraction on F, then it has a unique fixed point, right? Okay. So we're going to be focusing on Banach spaces. So if you have a closed subset of a Banach space, that subset inherits a metric, basically just from the norm on the Banach space. So a closed subset of a Banach space is a complete metric space. And those are the kinds of complete metric spaces we'll be interested in. If you rewrite the contraction condition in a Banach space, it looks like this, right? The metric is given in terms of the norm. And now we'd like some machinery for measuring contraction rates, right? And the derivative is the right, or is a great tool for that. So remember that if you have these Banach spaces, X and Y, you have a map between them. The map is Frechet differentiable at some point X. If there's a bounded linear operator from X to Y, so that we have this limit, basically saying that A is the best linear approximation of F at X, right? So this is the infinite dimensional version of notion of a derivative. So it's a theorem that if such an operator exists, that it's unique. So we can say, we can call A the derivative of F at X0. Okay? Now we're really interested in moving around the space. So you can think of the derivative as a map that associates with a point in your space, a bounded linear operator. And if that correspondence is continuous, then you say the map is C1. Right? Okay, you can study higher derivatives by just thinking of df now as a map from X into bounded linear operators from X to Y. Okay. Okay. So here's, in our talks this week, here's how we'll measure contraction rates. Okay, so you can prove a generalization of the mean value theorem. This says that, okay, so here this B is a ball, but when I have B, X, Y, this is the norm on bounded linear operators. So this says if on some ball I have a uniform bound on my derivative, okay, then my map F is Lipschitz on that ball with that bound on the derivative. Okay, so this is a nice way for measuring these contraction rates that you want for the contraction mapping theorem. Okay. So just summing all that up, you know, this says that if you can bound the derivative on your map less than 1, then your map is a contraction, right? Okay. So now what I want to do is state and prove a theorem that we're going to use for a posteriori analysis of nonlinear equations between Banach spaces. Okay, so this is our setup again. We have F between X and Y, C1. Okay, we have a point in our Banach space where the norm of F of X is not too big. That's what you call an approximate solution, approximate zero. We don't expect that F is a contraction, right? But, so we can look at the Newton method on Banach spaces, and it would be this, right? So your Your next approximate solution is your current approximate solution plus a perturbation, and you obtain that perturbation by solving this linear equation, right? Okay, so that suggests that maybe what you can do is study this Newton-like operator in a neighborhood of your approximate solution. Even though f might not be a contraction, you can hope that the Newton-like operator is a contraction near x bar. Okay. So the problem with this is that it's much too hard for me to do usually. So df as a function of x varies in probably a very nonlinear way. The inverse of that is even worse. So we cheat. We'll replace df inverse at an arbitrary point with just df inverse at the approximate solution. So that gives this Newton-like operator this new t, okay, where this is now a constant linear operator, not depending on x. Right? Yes, sir?
Another problem is that the Newton operator depends on the shape of the basing of attraction.
So we're going to have to find that.
Because if you have a ball, all the points in the ball are going to attract, but if the basing have a very strange shape,
then you try to find a ball in that shape, and that, yeah.
and this is the main problem too.
Sure. So this is going to be local, right? We're trying to do, we have the numerical approximation. We're trying to prove that there's a true solution nearby, so that's local. You'll see that we will get some more control than that, but not as much as you're asking for, okay? Okay, so this gives a Newton-like operator, but again, this is too hard, usually. So, you know, for Banach spaces, this may be an infinite dimensional linear operator, which could still be very hard to invert. So we might cheat again, okay? And we just replace, first, we'll replace our derivative, this constant linear operator, with just any linear operator we want, okay, as long as it's a bounded linear operator from x to y. And once we've done that, we'll replace the inverse of df with any operator we want that goes from y back to x. The first important thing, okay, this lets us define a Newton-like operator, which we're now free to study. It may or may not work out well, but we can certainly do this. And if A is 1 to 1, then fixed points of t correspond to zeros of f. Okay? Now, in fact, what you would like is that this A dagger somehow approximates your derivative, at least at the numerical solution or the approximate solution. And that A inverse at least approximates the approximate derivative. Okay, so now I have a lot of choices. I'm giving myself just a little bit of room to play with. Okay? Okay, so given these are my chess pieces. Okay, the pieces are now on the board. Given those pieces, here's the theorem that we'll use. Okay? This is essentially a Newton-Kantorovich theorem, but, well, yeah, it's a Newton-Kantorovich theorem that we're sort of tweaking to make it fit well with computer-assisted proof, right? We're setting up the hypotheses so that the objects in this theorem are things we can actually study with the computer, okay? So we have all the pieces I've just been talking about, the C1 map F, the approximate solution X bar, the linear operator A dagger, and the linear operator A, which should be 1 to 1. Okay? Now what I would like is 3 positive numbers and 1 positive function. Okay? So this is really scalar data. And this data should satisfy the following. Okay? I want this number y0 to be sum bound on my defect, but my defect preconditioned by A, okay? And this is nice because f goes from x to y, but A takes me back to x. So f times A is a map from x to itself. So there's some hope of using the contraction mapping theorem. Okay, this is basically measuring your defect, or this is what some people call a posteriori error. Now, I'd like Z0 to measure how good a job A does at inverting A dagger. So I multiply A dagger by A. I subtract from the identity. I take the norm in X. Okay, this is some number that says that A is either a very good approximate inverse or it isn't, right? Now I have a Z1. This is a number that measures how well does A dagger approximate DF, at least at my approximate solution X bar. And again, this is preconditioned by A, okay? All of this is just data that happens, these are fixed objects, the approximate solution, and then some fixed linear operators that I was allowed to choose. Now I have some local condition. I need like a Lipschitz bound on the first derivative, okay? So this function Z2, we want it to have the property that when I measure the difference between X bar and an arbitrary X on this ball, now R is a variable here, right? So I'm allowed to vary the ball on which I'm making this measurement. I need a bound on that measurement for all the balls of radius R. Okay?
So is that where you use the properties of the second derivative?
One way to get your hands on this is with the second derivative.
Yes.
But somehow you need some Lipschitz bound, at least on the first derivative. Okay? Okay, so given all this data, we define the function PR. Okay, it's just ZR times R squared minus 1 minus Z0 minus Z1 times R plus Y0. The theorem is that if we can find a positive R so that this function P of R is negative, then there's a unique X tilde in the ball, actually the open ball, BR, so that F of X tilde is 0. Okay, so these give us sufficient conditions for concluding that we have a 0 of F. Okay? Okay. A few remarks. In every example that we'll do this week, it can be arranged that this Z2 is polynomial, which makes P polynomial. Okay, so this is, for this reason, this is called the method of radii polynomials. And it reduces an infinite dimensional zero finding problem to a one-dimensional zero finding problem, zeros of P, right? Okay. In applications, what we look for is actually a whole interval of R's so that P of R is negative. So we'll have a smallest R, where we know that ball contains a unique solution, but we have a whole family of neighborhoods where this happens. So that gives us some isolation, some lower bound on this trapping region that you're talking about. Although certainly if the trapping region is, this can only give us the biggest ball about the approximate solution, right, at best. Now you can see since P0 is Y0, and since P goes to infinity as R goes to infinity, R minus certainly can't be 0, and R plus can't be infinity. This will be some interval away from 0 and less than infinity. Okay, so this R minus, the left end of I, gives you the sharpest, or it gives you sharp bounds on your error. This is a very small ball about your approximate solution where you know you have a true solution. And the R plus gives you isolation bound. This is another ball where you know you have uniqueness. Okay, so there are no other solutions in this ball of size R star. And this can be helpful. Not to have just one neighborhood where you have existence and uniqueness, but to have a very sharp neighborhood and also some isolation.
One question. It is possible that when we have a map from the finite space, that the inverse of the derivative cannot be unique, that we have
the inverse, if it exists, is unique, right?
But if the operator is a bounded operator.
For bounded linear operators, we'll have a unique inverse. Maybe we have no inverse, but if there's an inverse, there's just one, right? Okay, thanks. All right, I'd like to go through the proof of this theorem, okay, because this is going to be the workhorse for our entire workshop. And, well, the proof is not so hard, okay?
Could you recall, please, the sentence of the theorem?
Okay?
Define the function? Yeah, okay. Thank you.
Absolutely. Okay, so we've defined this function, right? So now assume I have an r where it's negative. Okay, we're fixing an r so that p of r is less than 0. All right? Now I can define an operator t on the closed ball of radius r about my approximate solution x bar as this Newton-like operator, x minus a f of x, okay, for everybody in this ball. Okay, and the way the proof is going to go is to try to show that t, to try to use the Banach fixed point theorem. So I want to show that t maps br into itself. In fact, it's going to map into the interior. Then we'll want to show that t is a contraction on this closed ball. If we can do that, then since the closed ball is a complete metric space, if we have this is a contraction, we'll have a unique fixed point of t. Okay, and then since a is 1 to 1, a unique fixed point of t gives us a unique 0 of f. Okay, so that's the strategy. So the first thing to see is that t is as regular as f is. And the formula for the derivative of t is just the identity minus a df. Okay, so that's going to work for everybody in the ball. So then we can try to bound the norm of the derivative of t. Okay, that's of course the norm. We just plug in this formula here and try to estimate. We'll use the triangle inequality twice. So I'll add and subtract a times a dagger, and then add and subtract a times df at x bar. Okay, so I started with the identity, then minus a times a dagger, plus a times a dagger, minus a df x bar, plus a df x bar, then minus the a times df that I'm stuck with from the definition of the operator, and then the triangle inequality. But then these are exactly the quantities, I've set myself up to have bounds on these. This is z0, z1, and z2, right? z2 times r. Okay, so now since PR is negative, right, let's look at what that means. Well, I'm going to take this r times minus 1, I'll have a minus r, I'll move it to the other side. These other negative guys are positive. So I have an expression like this. Okay, let's divide by r. Now everything in sight is positive, so if this quantity plus y over r is less than 1, then individually they're less than 1. Okay? But this quantity over here, this is our bound for the derivative. Okay, so this is precisely telling us that the derivative is less than or equal to this this is our contraction constant, and it's strictly less than 1. Okay? Now it doesn't really help us yet until we know that the thing maps the ball into itself. But the rest of the theorem is going to use this estimate on the derivative, every chance we get. So I'd like to show that t maps the ball into itself. So I pick a point in the ball, I look at t of that point, and then I measure how far away I am from x bar. Okay? So I need to bound this quantity. I'll add and subtract t of x bar. This is just a times f of x bar. Okay? And then for this, we'll use the mean value inequality. Okay? So again, our hypotheses give us a bound on this quantity, and this is what we just bounded. in the previous slide. So we have this, right? But x minus x bar is less than r. You distribute the r. You're looking at this polynomial, and the argument from the previous slide says, well, if PR is less than 0, then this thing is less than r. Okay? And actually, if you think about taking an x right on the boundary, this is a closed ball, this is saying something on the boundary actually goes inside, so that the t is taking a closed ball at least into its interior. Okay? But certainly we're taking the closed ball into itself. Okay, so now we have a mapping defined, from a complete metric space into itself. And, you basically, if you pick x and y's and b, you look at their difference, mean value inequality again, says that we're done, right? So this is a strict contraction on a complete metric space. Okay, and as I said, the fixed point, the unique fixed point, is actually not on the boundary, which is just worth noting, okay? Okay, so once you have a fixed point, since A is 1 to 1, we actually have a unique 0 of f. So this is this theorem, okay? And this will be the workhorse of this workshop. We'll solve a number of, I think, interesting applied problems using this setup, okay? Now, Renato asked about second derivatives. So I was kind of asking for a lot. I was asking for this map to be defined on all of the Banach space X. Maybe it's only defined on an open space, open subset. If that's true, you can sort of localize this theorem. Okay, so especially if f is C2, you can look for a uniform bound of your second derivative on some large ball, radius r star, that you get to pick. All right? If you can bound the second derivative on such a ball, then in any smaller ball, you have a bound like this. Okay? Okay, so in that case, your z2 is just a constant function, but a constant function only defined for r bigger than 0 and less than r star. And so then your p is only defined. But in this case, your p is quadratic, which is, of course, your favorite polynomials, right? Okay. And now the proof goes through just like before. Okay. So to use a theorem like this, to do a computer-assisted proof, let me just recap, because I feel like I'm going kind of fast, and it's a lot of stuff. But so we need to do some computations, right? We want an approximate solution. It was again, in our talks, we'll be using computers to get this approximate solution. We need an approximation of the derivative. Again, we can use, well, both computers and pen and paper to get this. Then we need to approximately invert this A dagger. And in infinite dimensions, so I'm going to do some finite dimensional examples now. But when Jean-Philippe talks about infinite dimensional examples, you'll use your understanding of the asymptotics of the derivative actually to define these A and A dagger. So there'll be more about that later. But the other thing you need that I haven't really said anything about at all, well, it's implied, okay, but you need the ability to check some bounds like this. That the norm of something is less than something else, right? You're going to want to do this on the computer. And so this is where the interval arithmetic comes in. Okay, so I'm not going to say too much about interval arithmetic. There are a lot of experts on interval arithmetic here. So, yeah. On the other hand, if you've never seen interval arithmetic before, I just want to say enough about it to make it seem kind of plausible. Okay, so interval arithmetic is software that lets you manage hardware round-off errors, right? So the digital computer doesn't really add numbers, right? It does something almost like addition, almost like subtraction, almost like multiplication, right? Even, numbers like a third, this has no floating point representation exactly on the computer. You can't even put this number in the computer, right? But what you could do is you could take 1 and divide it by 3 and round down, and 1 and divide by 3 and round up, and now you would have an enclosure of 1/3 in terms of floating point numbers. So this is a theorem, computer-assisted proof, right? That 1/3 is between this number and this number, right? So this is the kind of thing you could hope to do with the computer. So that's just, representing a number. If you start to add them, it's even worse, of course. But again, here's a computer-assisted theorem that 1/2 plus 1/3 plus 1/4 plus 1/5 is between these two floating point numbers, okay? Maybe as a mathematician, this seems like an inelegant way to think about numbers, but the great thing about floating point arithmetic is it's blindingly fast. Okay, so modern computers are fantastically good at doing this, right? So we would like to use that ability, that speed of the computer, and this is what we're willing to give up to use that floating point arithmetic, okay? So here's a theorem you could get. 1/2 plus 1/3 plus 1/4 plus 1/5 is less than or equal to this number, right? And that's the kind of thing I need in my theorem. My theorem, I need some complicated expression is less than or equal to some number, right? This is the kind of thing you could hope to get out of a computer using interval arithmetic, okay? Okay, another thing that good interval arithmetic packages can do is they can bound the ranges of the usual functions. So for example, I could ask a good interval arithmetic package, what is cosine of the interval minus 0.1 to 0.1, and I would get an answer like this back, right? So I can't compute cosine of an interval, but I can enclose cosine of an interval, or something like this, right? 1 over the square root of some number minus some interval, and you can see here actually it's not so good, this enclosure. Okay, so you have to be careful with this stuff. It's not a magic solution to all our problems. Sometimes this can really be a disaster, right? But these are the kind of things you can do, and they're at least correct. So the package, we use mostly IntLab with MATLAB to do interval arithmetic, but there are also C++ packages. There are Julia libraries. Julia libraries, I think, written by maybe some of the people in this room, or yeah? Okay. So people here are experts on this, right? Okay. So let me do an example of a computer-assisted proof, something very simple, using the setup I just described. Okay? Let's prove, this is like the first problem in any book on numerical analysis, right? We've all lectured about this problem. A fixed point of cosine x, that's solve cosine x equals x, right? Okay, so if I use Newton's method to try to find a 0 of cosine x minus x, and I start maybe at 0, I picked that just out of thin air. Maybe you like some other number better, but I picked 0. 5 steps, I get this as my approximate solution to that fixed point problem. If I take cosine of this number minus this number, my computer says the answer is 0, which is of course a lie, but that's what the computer says. So I'm close though. I'm so close I've tricked the computer, right? So we'll use this radii polynomial setup for cosine x minus x. So first of all, the derivative in this case is pretty easy to compute. The second derivative, pretty easy to compute. Okay? Okay, I'm going to let a dagger, so a linear operator on the line, it's just a number, right? So let a dagger be this number. How do I get this number? I just did a floating point evaluation of the sine function at my approximate solution. So no interval arithmetic, okay? This is just represented as floating point. Now my a will be this number. So the inverse of a linear operator on the line is the reciprocal. So I just compute 1 over a. Again, no interval arithmetic, just in floating point numbers. This number isn't 1 over that number, but it's pretty close, right? Computers do that pretty okay. Okay, so there's x bar, a dagger, a. I'm going to pick somewhat arbitrarily an r star is 0.1. I'm going to localize my problem on this number plus or minus 0.1. And then I'm going to bound the second derivative on that interval just using interval arithmetic. So I just plug that interval into cosine, take the absolute value, a good interval arithmetic package comes back to me with this bound on my second derivative. Okay? So this is my data for that theorem, right? Okay. Now I can compute. Now things have to start happening with interval arithmetic. I need to enclose. I take x bar to be an interval of width 0. I compute f of that. I multiply that by a, treating everything as intervals and take the absolute value. I get this answer for my bound on my defect. That's the y0 bound. Okay? The a times a dagger minus 1, similar, right? I'm multiplying two numbers together, taking them away from 1, I get something in quite a small interval containing 0. Same df, a bar minus df. Here, you're taking a interval computation of the derivative, and then you take away from that your approximate derivative.
Yeah, I mean, all of those are good, but the m is not great.
The m is not great, and you'll see worse than this, but it's a quadratic term. So m is appearing with something, an r squared, where r might be 10 to the negative 16. 10 to the negative 16 squared is quite small, and then this is not so bad, right? Yeah. Okay, so, and then here's our z2 bound. I define this function to be just, say, the right end of this interval, but only for r's less than 0.1, okay? Because this estimate only makes sense on that interval near x bar, okay? Okay, now it's just the quadratic formula, right? To find the zeros of this, and yeah, we get pretty good results, right? So if r is any number in this interval from 1.327 times 10 to the minus 16 all the way to 0.1, then this polynomial is negative, okay? So you can conclude that there's a unique fixed point, x star, and x star is in here, plus or minus this, very small number. But it's also unique in a much larger neighborhood, right? X bar plus or minus 0.1. Okay? Where am I on time? What time is it?
4:47.
Great. Great. Yes?
You use higher precision. Does it make sense?
Yes. You go to multiple precision. You can make this number close to whatever your machine epsilon is for the precision that you're working with. So in principle, you could make this as small as you wish, but multiple precision is way slower than hardware arithmetic. But yeah, you can improve this, of course. Mm-hmm.
Well, this problem is not going to be...
This problem is not so stiff, right? Yeah. Okay, let's do it again. Because I know that there are people in the audience who are really interested in interval arithmetic and have worked on these things before. I want to compare this approach to another approach, since I seem to have plenty of time. Okay? So the thing that I remember from teaching numerical analysis is that this is actually a contraction near that fixed point. So everything I just did was, maybe I used a club to, open an orange or something, right? What if we try to do this with the contraction mapping theorem? So, here's a shot at that. I'm going to pick an R. You'll see in a minute why I pick this R. But I'm just going to pick 1.6 times machine epsilon. Okay, machine epsilon is 2 to the minus 52, which is about 2.2 times 10 to the minus 16. And I'm going to define a ball about my approximate solution whose radius is that r. Okay? And that looks like this. Now I can use interval arithmetic to check. That should say subset. Okay, it says equals, but it should say subset. When I'm saying equals here, what I mean is that if I compute cosine of that interval, my software returns for me this interval, which means I know that if x is in B, cosine of x is an element of this interval. Okay, but that's the interval I started with. So cosine x is mapping that B into B. Okay? Now I can look at the derivative, which is just a derivative of cosine is negative sign, but with the absolute value, it's just sine. So I can take now sine of this interval. I see that that's contained in an interval which is bounded away from 1. Okay, so I now have a map from a complete metric space, namely this set into itself. I have the derivative less than 1. So there's a unique fixed point in B by the contraction mapping theorem. And this argument was maybe a lot simpler than what I just did. But if I try again with r equals 1.5 times machine epsilon, the proof fails. Okay, my interval arithmetic package can't verify that cosine of that smaller b is, goes into itself. Now, the number that I got with this radii polynomial approach was substantially smaller than 1.6 times machine epsilon. It was actually quite a bit smaller than machine epsilon even. I was at about 1.3 times 10 to the minus 16. Okay, so that's a lot smaller than the 1.5 where this fails. Now again, I know there are experts in the room, so people will say, sure, but you should have done a Newton-Krychak or some kind of interval Newton. Okay, so I did. And of course, the interval Newton works a little better. The proof works for 1.1 times machine epsilon, but fails for machine epsilon. So the radii polynomial still gave me substantially better error bounds. And it should, because, okay, let me not get ahead of myself. So any sort of interval method, you're checking estimates using interval arithmetic. Machine precision is going to be pretty close to the best you could ever hope to do, right? On the other hand, with the method of radii polynomials, you don't have to guess a neighborhood and then check that the ball maps into itself. You don't have to iterate, do some iterative procedure to find the right neighborhood. You just take your data, right? Your approximate solution, approximate derivative, approximate inverse of the approximate derivative. And given that data, you find every neighborhood where this thing is a contraction. Okay? So it's a little more work, but you get a little more out of it. Okay? So if we're being honest, the downside is that it's more work. Okay? You have to, check more inequalities. You have to do some estimates of second derivatives and things like this. But if you're doing a problem like some of the things we'll talk about later this week, where you're building a computer-assisted proof on another computer-assisted proof, on another computer-assisted proof, on another computer-assisted proof, every multiple of machine epsilon you lose, you're never going to get back. Okay? So if you can be greedy about them, this can really help sometimes, especially after 10,000 steps. Okay? It starts to really, it can matter. The other thing is if you study infinite dimensional versions of Newton-Krychak, most of the versions that I know, and I may have missed some, I admit that, but the versions that I've seen are formulated in a Hilbert space. Okay, and we're going to work in spaces that aren't Hilbert spaces. They'll be just Banach spaces. Okay, so if I don't need that Hilbert space structure, that can be an advantage sometimes. Okay. Okay, I think I still have some time, right? What time is it? Great. All right. So let me finish up talking about, a slightly less trivial problem. And this is a problem that actually both of us will come back to several times in the next few days. So this is a restricted 4-body problem that I actually should thank Jaime for introducing me to some number of years ago at, I believe, a tavern in Penn Station, right? So the idea is that you have 3 massive bodies. They're in an equilateral triangle configuration, so you know that's a relative equilibrium of the 3-body problem. You change to co-rotating coordinates so that these become singularities of your vector field, and you're interested in the motion of a 4th massless body. And usually people normalize so that the masses add up to 1. Okay? So this is the vector field for this problem where we have all these 1 over r, r to the 2/3 power, minus 2/3 power kind of nonlinearity. All right? So understanding the dynamics of this is a very interesting question, I think. So the first thing we could talk about, or should talk about, are equilibrium solutions, right? So an equilibrium solution satisfies these equations, but this simplifies a lot because even I can solve W equals 0 and V equals to 0 in my head, and that eliminates this and this. So you're really looking for zeros of this map from the plane to itself, okay? Okay, so it's just a function of 2 variables, 2 equations and 2 unknowns. Surprisingly, maybe not surprisingly, but it was interesting to me when I started to read about this that it's actually quite hard to understand the equilibrium set for this problem, okay? It's not so easy. Okay, what do I want to do? I want to do a computer-assisted proof just for an equilibrium solution of this 4-body problem. Okay, so this is still an easy finite dimensional problem, but maybe in an application that we care about. So I'll norm my space with this norm because this is a fantastic norm for the computer. The computer sort of loses nothing when it computes this norm, right? Once you pick this norm, this is the induced matrix norm, and then the induced norm on bilinear forms is this. So, my radii polynomials involved all these norms of matrices, norms of bilinear forms. Okay, and you can just program those norms into your computer using these formulas and then evaluate them with interval arithmetic when needed. Okay? So, numerical work on this by Carlos Samo, wonderful paper, 1977, says that depending on the value of the masses, this problem has 8 or 9 or 10 equilibrium solutions. Okay? I think Carlos convinced everyone of this, but there was no proof until recently. Whoops, here's a picture. So this is equal masses, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equilibria. This is for non-equal masses. We've moved away, more mass in M1. 2 of these equilibria have collapsed and disappeared, and now you're left with 8. Okay? This is sort of typically what the equilibria set looks like. Okay, so Leandro has recently proved, there are about 3 papers on this, that Carlos was right, which doesn't surprise anybody, but it's nice to have a proof, right? His proof is computer assisted, and he proved for any values of M1, M2, M3, adding to 1, there are always 8, 9, or 10, and that the curve where there are only 9 is an analytic curve. Okay? This is a very nice result. But I'll do something much less ambitious with the few remaining minutes of this talk. Just for a particular value of the masses, I'll try to show that there's a saddle focus equilibrium for this problem, and I really want to figure out where it is. Okay? Why the interest in saddle focus equilibria? Well, if you have a Hamiltonian on R4 like this, and you have a saddle focus equilibrium, it means complex conjugate unstable, complex conjugate stable eigenvalues. If you have a connecting orbit from that equilibrium back to itself, which can't be transverse in this sort of full problem, but it can be transverse in the energy section, which is, you know, the energy manifold is three-dimensional. Those are two-dimensional manifolds intersecting inside a three-dimensional manifold that can be transverse. If you have such a connecting orbit, then there's a tube of periodic orbits that accumulates to that connecting orbit, okay? And that those periodic orbits are parameterized by energy. And this is called a blue sky catastrophe, okay? So another theorem with the same hypotheses is that if you have this transverse homoclinic, then there's actually a chaotic horseshoe near that homoclinic. It's a nice point to stop and think about why you might ever want to do a computer-assisted proof in the first place, okay? So these are fantastic theorems from nonlinear analysis whose hypotheses are quite difficult to verify in particular problems. If you hand me a four-dimensional Hamiltonian system, and even if I know it has a saddle focus equilibrium, it can be very hard for me to prove that there's a transverse connecting orbit. Okay? Sometimes it can be done with variational methods, but sometimes it's very difficult. But if, with the assistance of a computer, you could prove the existence of a single transverse homoclinic, you now have uncountably many periodic orbits accumulating to that, and you have chaos near that homoclinic. So for the cost of that computer-assisted proof, you get a great deal of additional information. Okay, so this is why I'm interested. It's one reason I'm interested in these kinds of computations. Okay? But if you were going to try to prove something like this, the first thing you would need is to know there was a saddle focus equilibrium, which maybe you could prove by hand, but maybe you can't. Okay? So here's a computer-assisted theorem, slightly less trivial than the cosine x equals x. So for these masses, the restricted four-body problem has a saddle focus equilibrium. In a ball about this point, that ball is of radius 3 times 10 to the minus 15. Okay? This is a theorem. How do we prove this? Prove it just like the earlier problem. So here's the proof. So we do a Newton method to get a numerical approximate, a numerical zero, right? Then I compute using floating point arithmetic, no intervals. Just, you know, I find the formulas for the derivative, I evaluate those formulas. Now I have a matrix of numbers, right? This isn't the derivative, but it's very close to the derivative. Now using the computer, I invert that matrix. This A is, of course, not the inverse of this matrix, but it's pretty close, right? Okay. This is where maybe you could imagine if you were in 10 or 50 or 1,000 dimensions, it's nice to not to have to invert interval matrices, right? Just doing an approximate inverse of an approximate derivative can be nice. Okay. And then using interval arithmetic, I can check bounds. Well, wait, getting ahead of myself again. I can compute the norm of this matrix smaller than this number. Okay? Okay. So now I just I evaluate this function with these inputs, now using interval arithmetic and multiplying by this matrix. I get this enclosure. You can see if you take the max norm of that, everything's less than or equal to this, times 10 to the minus 14, right? So I'm going to pick y0 as this number times 10 to the minus 14. So see, this is how I'm using the interval arithmetic to produce these numbers that I need in this theorem. Okay, so this is now the theorem. F of that xy that I picked times this a that I picked, take the norm, it's less than this y0 that I also picked. Okay. Now I can multiply those two matrices, but do it now with interval arithmetic, subtract the result from the identity, take the matrix norm, and I get this interval enclosure. I take the norm of that, I get this result. So I'll pick z0 to be this number. Yeah? Same thing for a dagger minus df. Now I evaluate this formula using interval arithmetic and take it from that floating point matrix. Take the norm of that. I can take z1 to be this number. Now, you know, in infinite dimensions, this is going to be more work, and this is what John Philippe will move into in the next talk. Life is a little easier in finite dimensions, right? But these kinds of things will require more thinking combined with computing like this when we do harder problems. Okay. The last thing is I need this bound on the second derivative, so I'll take a small ball, I'll do a computer-assisted estimate. Again, you can complain, this is not that good an enclosure, and it's a pretty big number, but it's okay because it's going to get hit by r squared, right? Okay, so I have this. So I take z2 to be this number, but only if r is less than r star. Okay. Well, now again, it's the quadratic formula to check that PR is less than 0 on this interval. So from about 3 times 10 to the minus 15 all the way out to 0.1. But a lot of this is nonsense because my second derivative bound only holds on a ball of 10 to the minus 6. So I need to throw the appropriate stuff away. And this is my result. Okay? So in a ball of about 3 times, well, 10 to the minus 15, there is a unique solution near my approximate solution, and there are no other zeros in a ball of size 10 to the minus 6. Okay. Yeah. So that was the proof. Okay, so just a few final comments. I just did an equilibrium of a 4-dimensional problem. That's an invariant set, but there are much more interesting invariant sets than that, and they require more work, right? And so that's what we'll be getting into in the next days. Okay, what I'm going to talk about tomorrow, I'll actually move for one lecture kind of away from computer-assisted proof and talk about just computing. I'll talk about computing invariant manifolds and then growing those invariant manifolds, but doing it in a way where I can validate all the computations. Along the way, I'll find a lot of numerical connecting orbits, and I'd like to prove some of those connecting orbits are there. So tomorrow, more computations. Then Friday, I'll come back and validate some of these computations. Okay? But before that, John Philippe, the next lecture today is going to be about some infinite dimensional problems that you can solve, infinite dimensional problems actually for PDEs, that you can solve using this strategy that I've outlined this afternoon. Okay? So, thanks for listening, guys.
Bien, ¿hay preguntas para esta primera parte de la exposición de Jason?
Tengo una pregunta de ignorancia. This is just about ignorance, because you were telling us about you have the A dagger, and then you need to compute an approximation of the inverse. Of course, in the finite dimensional case, you can just invert numerically, and that is going to be kind of an approximation of the inverse. I assume you are gonna use some other approximations, like especially in infinite dimensional spaces, like trying to use a kind of a clever approximation to the inverse without doing any inverse at all?
No. What we will do is we'll try to break the problem into a finite dimensional part, which we treat this way, and an infinite dimensional part, which must be treated more by hand, asymptotics, right? For the finite dimensional part, we'll invert the finite dimensional part of the inverse numerically, which gives us a good approximate inverse. For the infinite dimensional part, we have to do something with asymptotics to get a good approximate inverse in infinite dimensions.
Okay.
This will be the idea. Yeah.
¿Hay más preguntas?
Actually, I have one. I might be, at least I should wait maybe for tomorrow, but what's the difference about these techniques in comparison to Bernd and Kim Kyosinga does. So what I'm trying to say is that you're going to compute some manifolds.
Yes.
Stable or unstable, which is basically doing some continuation techniques, right?
No, I'll do formal power series.
I see.
Yes.
So that's the difference.
So I think even the non-rigorous numerics that I'll do will be somewhat novel.
I see.
I hope.
All right.
Ok, bueno, si no hay más preguntas, propongo que tomemos un descanso de 15 minutos. Aquí hay café, hay galletas, también a lo mejor alguien quiere ir a un refrigerio o algo así. Y en 15 minutos seguimos con la parte de la política. También las personas que van a anotarse en la lista, si quieren constancia sobre todo.